Picture this. You're staring at a terminal window, watching literally millions of lines of simulation data scroll by at warp speed. And you're just sitting there, wondering how on earth you're supposed to spot the one tiny error causing your entire hardware design to fail. If you work in a hardware verification, you know this chaos intimately, right? You are basically trying to find a single bug hidden in millions of simulation cycles. Well, welcome to this explainer. Because today, we are going to tackle that exact problem by demystifying UVM reporting. Now, UVM, the Universal Verification Methodology, is the IEEE standard that powers ASIC and large FPGA verification. But today, we aren't just going to look at its reporting infrastructure as some dry, boring technical spec. We're going to see it for what it truly is, your ultimate bug filtration system. Okay, let's dive right into this. Here's our roadmap for this explainer. We'll hit the debugging challenge, core macros, verbosity levels, formatting actions, and finally, wrap up with some real-world industry strategies. Part 1, the debugging challenge. Finding the signal in all that noise. So, why do we even need a complex reporting system in the first place? Look, generating massive log files is incredibly easy. Dumping millions of lines of text from your test bench is trivial. Finding the actual bug? That's the hard part. When you have drivers, monitors, and scoreboards all running concurrently, you absolutely need a strategic filtering mechanism to separate those crucial signals from the deafening test bench noise. Moving to Section 2, core macros, or as I like to call them, the 4 horsemen of reporting. UVM gives us 4 distinct severity-based tools to cut through that noise. UVM info, UVM warning, UVM error, and UVM fatal. And here is the absolutely crucial point. These are not just your standard print statements. UVM's reporting infrastructure automatically tracks the file and the exact line number for you. So when a message pops up, you know exactly where in your code it originated. No more guessing which component threw the error. For the basic UVM info macro, you just need 3 things. An ID string, which acts kind of like a tag, a message string detailing what actually happened, and a verbosity level. That ID string is a real game changer because it allows you to easily filter messages by specific categories or features within your test bench later on. Now take a look at the syntax for the other 3 macros, UVM warning, UVM error, and UVM fatal. Do you notice anything missing? There's no verbosity argument. UVM enforces a default verbosity setting of UVM none for these critical messages. This guarantees they can never be mistakenly hidden when you turn down the simulation's overall verbosity filter. Basically, if there's an error, UVM makes absolutely sure you see it. Let's pause here for a second because I really want to emphasize a vital distinction between UVM error and UVM fatal. A UVM error flags a real problem, like a mismatch in your scoreboard, but it lets the simulation continue. This is awesome because it lets you gather more data and potentially find multiple bugs in a single run, subject to a quick count limit, of course. But a UVM fatal? That means you've hit a problem from which the simulation simply cannot recover. It exits immediately at 0 delay via a $finish command. You'd use fatal for fundamental setup failures, like, say, a missing virtual interface. All right, Section 3, verbosity levels. This is all about controlling the volume. Think of it like this. If the core macros are the messages themselves, verbosity levels are your volume control. When you write a UVM info message, you assign it a level, let's say UVM high. Then, when you run your simulation, you set a global or a component-specific threshold. If your simulation threshold is set to UVM medium, well, that UVM high message is silently filtered out. It never even hits a log file. This is brilliant because it lets you write incredibly detailed debug messages into your code, but keep your log files clean and manageable during regression testing. And the best part, you don't have to delete a single line of code. And these levels aren't just arbitrary words, they are strictly defined constants within the methodology, ranging from UVM none all the way up to UVM full. This standardization is exactly what allows UVM components written by completely different teams, or even different companies, to interoperate seamlessly. Section 4, formatting actions. We are going way beyond just printing to the console here. So UVM reports are deeply tied to specific test bench actions. Each report's severity actually executes one or more actions. For instance, when a UVM_error is triggered, it doesn't just print some text. It triggers a UVM_count action, which increments a quit counter. If your simulation hits a predefined maximum number of errors, that action escalates to a UVM_exit, safely terminating the run. You can even configure an action to trigger a UVM log that sends specific severities or even specific IDs to separate dedicated text files instead of cluttering up your main standard output. Pretty slick, right? Finally, Section 5, Industry Strategies. Let's see how the pros apply this in the real world. So how do verification engineers actually apply this stuff in complex architectures? Well, first, we have to talk about UVM phases. UVM phases make sure all your components are synchronized. You've got non-time-consuming phases like build and connect, which execute right at time 0, and then the time-consuming run phase where actual stimulus is driven. Your reporting strategy needs to be phase-aware. For example, if a critical configuration is missing during the top-down build phase, you should throw a UVM fatal right then and there. There's literally no point in starting the simulation. Conversely, UVM info is heavily utilized during that time-consuming run phase to log transaction data as it flows through your drivers and monitors. And a quick but massive side note on the run phase. UVM uses an objection mechanism. If your components don't raise an objection during the run phase, your test bench will just immediately jump straight to the extract phase at time 0 without actually driving any stimulus at all. You can easily use your reporting macros to debug why a simulation bailed on you prematurely just by checking exactly where objections were raised or dropped. Okay, before we wrap up, I want to share a massive architectural pro tip from verification expert Chen Ben-Harouche. A huge source of configuration bugs and fatal errors actually comes from relying way too heavily on UVM configuration DB. Because UVM configuration DB requires a component context and a string-based path, it is notorious for causing fatal errors when you try to pass data to non-components, like sequences. This usually forces engineers into using awkward workarounds, like the p-sequencer pattern. Chen's advice? Transition to UVM resource DB. It uses a straightforward string for scoping and allows any entity to store and retrieve data cleanly. It completely eliminates the need for those p-sequencer workarounds, making your test bench vastly cleaner and way less prone to configuration fatals. It's a real game changer. So by mastering these reporting macros, managing your verbosity levels, understanding phase-aware actions, and utilizing robust databases like UVM Resource DB, you can finally stop fighting your test bench and start fighting the actual bugs in your hardware. I'll lead you with this final thought. The untapped power of UVM is waiting. Are you ready to level up your test